let us start this lecture with a thought process from Albert Einstein. He says, try not to become a man of success, but rather try to become a man of value. Of course, in today's world, people won't look at his statement, but which is eternal. So, in the last lecture, basically we looked at the soot mechanism of the jet diffusion flame and also the diffusion flame general, and later on we moved into the initiation of discussion on the liquid fuel combustion, right, and we will continue that discussion on that. And let me just tell you that we need to basically convert the bulk liquid into spray. In other words, arrays of spray is basically arrays of droplet size of various kind, and such that it will be helpful for the higher rate of combustion. Why? I will just give an example. 3 mm diameter of droplet, right? If I want to convert into, of course, hypothetically 30 micron, what will be the 30 micron diameter? Like let us say there is a big droplet 3 mm, I will convert into 30 micron, and it will be like something 1 million, right? And if you look at the surface area will be increased by tremendously. So, therefore, I can enhance the heat release rate per unit volume for the same amount of fuel being burnt, or for burning the same amount of fuel. So, that is the beauty of this thing, but however, it is quite complex in nature, and not only atomization, but also the combustion process involved. I will just try to give you overall picture of the liquid oxygen and gaseous hydrogen combustion in a rocket engine. This is a very simplified one. If you look at this, I have shown here, and it is having a liquid oxygen jet, which is the liquid itself. This is the liquid, right, liquid oxygen, and this is remaining intact. However, when the hydrogen is moving around, it is trying to smear out some of the larger ligaments. These are ligaments, which will be coming out of that, and then this of course will be interacting with the gaseous hydrogen and other things. They may collide each other, then they will be subjected to decrease in their diameter. And this, keep in mind that these are not spherical in shape ligaments, may not be, but generally no. This entanglement of ligament from the bulk liquid is known as the primary atomization, and later on these ligaments will be converted into droplets, and then it will be interacting with the cell. Sometimes the droplet may coalesce, but not near this place, but maybe far away. Momentum will be very much reduced, not there. They may coalesce also. That means small droplet can combine, two small droplets or many droplets will combine to bigger droplets. That will occur only when the momentum in this thing is not there and combustion has not taken place. So, this is, if you look at, it is a quite complex process. Let me just start with the liquid injection. Injection is itself a problem. The gas injection another problem. One has to, of course, if there is a flame, if you look at this, a flame is here, of course, you will have to ignite, and then there will be some gasification, vaporization of the like front. These are the vaporizing front, right, I have shown. And then of course, the liquid will be heated up, and then the atomization, there can be a jet or there might be seed formation. Of course, here is not being shown, but there is a fan also, depending on the type of injectors, whatever. I am not discussing about type of injector, that will be another altogether very different subject. So, secondary atomization, I have told coalescence and collision can occur, right, in this case, and there will be a vaporization, droplet vaporization, gasification, some flame will be formed. I will be showing something how it will be going on. And beside this, there will be turbulent mixing, chemical kinetics, like which will be governing the reaction rate, turbulence and droplet interaction, and turbulence and reaction interactions, all those things will be coming to picture in the actual systems. Beside this, as there will be heat release, there will be expansion of the gases, and of course, the flow may separate because we want to enhance the mixing in the real system, then there will be flow separations, and all those things has to be modeled and understood. It is not that easy, it is quite complex process. So, I have just given you the bird's eye view of the liquid fuel combustion. Unlike gaseous fuel combustion, liquid fuel combustion is quite involved to understand and to model, right. And it is a two-phase flow. So, turbulent and then heat transfer, mass transfer, chemical kinetics, quite complex, and also the droplet size, the distribution will be changing, right, how will take, and all are random in nature. Keep in mind the droplet, the atomization process is random in nature. So, I will just give you some idea about that. Is let us say this is a atomizer, right, and jet is coming through this nozzle, right, this is your nozzle, and there is a atomization is taking place. There might be droplet dispersion, right, and there might be a droplet interaction. The droplet will be interacting with each other, there will be evaporation, and this is of course the envelope flame I have shown here kind of things. If you look at, there might be a situation where there is a several of droplets and they are very close each other, right, and they may together will be giving some vaporization of this thing, and then oxidizer will be coming over here, oxidizer, right, and this is coming fuel vapor, and this is a flame will be formed, right, and this is known as a group combustion or group flame. There might be a situation where a single droplet flame might be there, right, and there might be situation two droplets, burning droplet having flame together a little far away. So, there is a all permutation combination one can occur. Of course, this I have shown a flame in my lab itself, the liquid fuel combustion. You can see this is again a jet liquid fuel combustion. That is this a blue color, it is well mixed, and here of course the droplets are, and these are the path line where the droplet will be moving, that shows. It is not a very good image. However, if it is a high speed image, you can track the droplet, provided it is a bigger one. If it is small, it will be very difficult to track exactly, right, and bigger one you need not to, you should not have that, right. So, let us look at what will be happening. Happening is that there is a one situation is a single isolated droplet, right, one single droplet. This is your droplet, right. Of course, generally it will be spherical nature, right, and there might be as I told that there will be evaporation from the surface of the droplet, right. This is vapor, fuel vapor, and this will be oxidizer which will be coming, and then this is the flame which is formed, right. And there might be two droplets which are together having one flame. There might be some maybe 5 burning droplets which are together, right. And of course, if there is a number, then they call it a cluster or a cloud of the droplets, and this is known as a group combustion. Generally, in the homogeneity, the spray field with respect to density, drop, size and velocity, it is very difficult to get, right. And droplet burns in a collective manner referred to as a group combustion. You can say this as a basically group combustion. You can also call this as a 5, but generally 2 burning droplet, 3 burning droplet is very rare, like it will be. When it will be occurring? Where the number density, that means number of droplets per unit volume is very high. That means they are very close to each other, although I have magnified it so on, but they are very close to each other, each droplets. So, therefore, the group combustion will be taking place, and it can all permutation combination can take place, like you can have a fuel droplet, single isolated droplet combustion, 2 burning droplets and 5 burning, maybe 7, 9, 8, 6, whatever it may be also together. So, anything can happen, and all together. So, let us look at what is happening, the process of droplet combustion. once this fuel droplet is there, what you need to have is basically heat from the flame surface, right. If there is a droplet here, right, there should be some ignition source you will have to give, so that the heat will be coming out, right. It will be getting into this droplet, like let us say this is the heat source, heat source. So, some heat has to get into. Why it is required? Because it has to evaporate, right. It has to vaporize the liquid droplet. Right. And then fuel of course will be start boiling, means vaporizing rather, and there will be vaporization which will be occurring, right. And this vapor fuel vapors will be moving, of course this will be moving towards all the sides, right. And similarly this is a quiescent atmosphere, so therefore oxidizer will be coming towards that also, and whenever they will meet, right. So some kind of this flame, I can say this is your flame will be formed. So and fuel and oxidizer will be mixing at the surface of the flame. That means in this case the and this is occurring because of diffusions, and this is diffusion control, and reaction will be very fast, right, as compared to the time required for mixing. And then of course you will have to ignite, and if there is a flame already, there is no ignition, the flame will be giving you heat into the surface. This is heat. Heat will be getting into the surface of the droplet, and it will evaporating it, So the droplets will be getting evaporated due to the heat received from the flame once the flame is established. So what we will be doing? We will be basically looking at a single droplet combustion in our class, because it is very difficult to tackle the problems of the spray combustion. Later on we will be using this, how we will be using those results for analyzing the spray combustion, again within the limitation of one dimensional flow, right. So let us look at the single isolated droplet, and in first is the situation where droplet is there. This is your droplet having certain diameter, fuel vapor is going out, and then this is a quiescent atmosphere, therefore oxidizer will be coming in, right, from atmosphere, right. Now I will get a flame like this, right, and there is another situation where the droplet, this is the droplet, and I am getting a flame like that. I have shown you earlier a flame in my lab itself, but under what condition I should get? This is will be corresponding to the zero gravity condition, right, and this is earth gravity condition. Of course one can conduct experiment also the higher G as well, okay. And keep in mind that generally this will be problem which is complex as compared to the zero gravity condition, isn't it? Because here the flame is symmetric in nature, whereas here also it is symmetric, but it is symmetric with what? Will be along with this, not with this, right, along the vertical direction in this diagram, but not in a horizontal, right. And beside this, the this elongated flame is coming because of buoyancy. Now buoyancy effect has to be also taken care. And there is another situation which is a practical one, that where the flow will be there, right, or I can say this is oxidizer velocity which is moving, and then I will get a flame here, and this is your wake region, right, and this is your boundary of the flame. There will be boundary layer, hydrodynamic and also thermal, right. So this will be there, and this is also quite a complex in nature. What we will be doing, we will be basically trying to look at the droplet burning under the zero gravity condition, try to analyze it and use the data for the convective flow, because this is basically force convection, right, condition, and this is natural convection, right, condition, and this is the zero gravity. There will be some convection, but however it is some bulk fluid will be moving, but that will be radially it is going on. So, this is known as normal G, what you call 0 G, right, this is 0 G. And keep in mind that this distance, if I take from the center, or maybe I can take from center here. So, this distance, what I call, this is the flame standoff distance, RF is the flame standoff distance. If you look at that, is very important, and that will affect basically the how fast the droplet will be receding, means getting consumed, right. So, what are the factors that affect the shape of the flame front? This basically, as we have already discussed, condition under which combustion takes place. For the 0 G, this will be spherical flame front, no buoyancy effect, this is a spherical and symmetric also. Normal gravity is elongated due to natural convection, and force convection condition, flame aligned with the flow, because this is the flow which is taking place, it is aligned. And energy required to vaporize this liquid fuel is very important, because that will be governing how much fuel is vaporized and how it is moving out and then coming in contact with the oxidizer for forming a flame. So, QB is equal to delta HV plus CL Ts minus T infinity. If you look at the first term, is basically latent heat of vaporization, and the second term is the sensible enthalpy, and Ts is the what? The surface temperature, droplet or surface temperature, and T infinity is the ambient temperature. If you look at the, let us say, of course, here it will be very high, but you will have to look at when you started what will be the ambient. Like for example, far away from here, this will be T infinity, very far away from the droplet. Nearby it will be flame temperature, right, near the flame temperature, after that it will be receding. So, we will be analyzing this thing, and for that what we will say, let us look at a single droplet. We are considering the 0 G condition. Force convection condition, if you look at any practical combustor, will be force convection, because the flow will be coming and the droplet will be there, and then it will be, right. But single droplet, certainly no, you will have to conduct an experiment to understand the process. The array of droplet will be there and it will be moving, and each maybe droplet will be moving with their own velocities, but also the velocity will be changing across the cross section of the combustors, and as it moves it will also change. It is quite complex. Generally, force convection means is a practical situation, and this single droplet what we are discussing, do you think that it will be anywhere practical? No, right. It is only for our understanding or in experiment for research purposes we do. So, if you look at the droplet is here, and this is a symmetric in the sense along the phi direction, because it is spherical in nature droplet, and the phi direction and then the psi direction, that will be symmetric, and it will be varying only along the r direction, right. So, if you look at this distance is basically from here to this is the RS. RS is the droplet surface radius, right. This is basically I can say RS is the droplet surface, right. And this is your, as I told, RF is your flame stand up distance, because flame will be located at certain region that will be dictated by basically how fast this fuel is diffusing into the flames, and also the oxidizer being diffused and mixed. So, that will be dictated by that. And if you look at the region wise, and there will be inner region, right, in this portion, this is your inner region, right, and outer region will be here, I mean like outer region. So, in a region what will be happening? If you look at temperature, of course, from the surface temperature, this is your surface temperature, right, this will be surface temperature Ts, and it will be increasing to the flame temperature, and then after that it will be decreasing, and this will be something T infinity, right, ambient conditions. And similarly, if you look at the fuel mass fraction is decreasing, it will be maximum at the flame surface, sorry, and the droplet surface, and it will goes on decreasing, and then it becomes 0 at this location. And similarly, the oxidizer also will be mass fraction of the oxidizer will be decreasing, and it becomes 0 as the flame surface, and this is the flame sheet. And product, of course, will have peak value at the flame surface, because product is formed. And keep in mind that this is the approximation what we are doing, thin flame approximation. So, if you look at, this is basically the single droplet in a quiescent atmosphere. There is no disturbances, there is no flow, it is just quiescent atmosphere. So, if it is quiescent atmosphere, then, and also it is under 0 G condition, right. And I can, as I told earlier, that it is we can consider it as a one dimensional inviscid flow, right. There is no viscous effect we are considering. And we can assume that quasi steady state droplet vaporization or the burning is taking place. Keep in mind that this vapor which will be moving, right, that depends upon whether it is steady state or not, because of fact that what is happening, the rho f of the fuel, density of the fuel, right, will be far greater than the rho of the vapor, right, or the gas, whatever being, this gas, the fuel gets vaporized on the surface of the droplet, and then it moves, right. So, that density is very, very higher. So, if it is higher, so what you can say that dRs, right, I can write down dRs by dt will be very, very small, right, as compared to the velocity, the bulk velocity which it will be, gas will be moving, because the gas will be moving outwardly, right, with certain velocity, because it is due to the diffusion, right, which will be taking place, and also, right. So, therefore, this will be quasi steady state, this is not changing, it will be something few mm or not mm, even it will be micron per seconds. So, it is almost changing, but whereas this velocity will be higher order. So, therefore, it will be almost steady, quasi steady, we can't say it is a steady process, because the droplet size is decreasing as the burning is taking place. Okay. That decrease of the droplet size is quite small with respect to time as compared to the with which velocity will be moving. Okay. So, the droplet temperature is uniform, but which is not true, right, because at the center temperature will be different, at the surface it will be different, but we are assuming, otherwise you will have to solve the equation for the liquid or the droplet, inside that you will have to solve, but we are assuming it to be the uniform, which is not the case. Even if you conduct experiment, it is not possible. Okay. But however, simplicity we have done, and density of liquid fuel much higher than the gas phase, I have already told. fuel is a single component with no solubility of gases, because let us say diesel is a multi component fuel, right. So, there might be multi components fuel, like nowadays people are gasoline, they are adding some alcohol. So, then it is not that way, it is only single component fuel, there is no other gases which are being there in that, and otherwise there will be a lot of problems in that, like vortex will be formed, there is a quite complex phenomena, and flow velocities are assumed to be low, right. And single step irreversible reaction rate we will be using, which is basically, as I have told, this is the thin flame approximation, this is the thin flame, or you can say this is a thin flame, right, approximation we will be doing, and constant thermophysical properties as usual we do, unity Lewis number, right, and radiation heat transfer is neglected. So, these are the things we are making this assumption, and no other phase is formed in the liquid fuel droplet, right, because in the droplet there might be two phase, there might be solid particle or some other things. So, that is not there. So, with this we will stop over, and we will be discussing in the next lecture how to carry out this analysis. Okay, thank you very much.